Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 49, Liquids and Solids, Part 4. This is our last video in Chapter 10 of your textbook. Here are our objectives for today's video. Pause here. So a lot of you are familiar with something called the heat of vaporization, which we'll get into in about a minute, which just is the amount of heat that you have to add when something's at its boiling point. And the reason why you're all familiar with it is because you've all stared at a pot of water wondering when it's going to boil when you're trying to make pasta or tea or coffee or whatever. But there's also something similar when we have stuff that is freezing. So let's just say I've got a sample of ice and I heat it. It's going to reach 0 degrees Celsius, and then it's going to hang out there for a little bit because we need to break some intermolecular forces before it starts melting. That is called the heat of fusion. You can actually quantify it, and it will have typically units of kilojoules per mole or kilojoules per gram. Pause here. And then heat of vaporization is really the same thing, just the difference is we're going to go from the liquid to solid state instead of the solid to liquid state. The heat of vaporization is going to always be greater than the heat of fusion because when you go from the liquid to the gas phase, you have to break every single intermolecular force, whereas when you go from the solid to liquid phase, you only have to break some of them. Pause here, you only need a rough sketch of the picture. So a heating curve, and if all goes well and we're able to have in-person instruction, you may have had made one of these by the point in time that you've watched the video. Fingers crossed, we'll see what happens. But heating curve shows how temperature change as a function of heat added. And here's an example of a perfect heating curve. If you've actually done the experiment in class, you'll see that yours probably looks kind of like this, but certainly not as perfect as this one does. So this is just theoretical. So what happens is that you see that you've got this linear increase in temperature until you reach the freezing point, and then we have a plateau, and that plateau is because of the heat of fusion. And then we have another linear line with a different slope as the first line, that's important. And then we have a much larger plateau because of the heat of fusion. And then we have a third increase. Again, we've got different slopes of the three linear lines, the ice, water, gas labels here, and that's because the specific heat capacities are different in the different phases. Specific heat capacity, I hope by this point in time that you've done an experiment on it, it's just the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. Pause here. All right, so I just put down in notes what I just said out loud. The reason why it can be 1 degree Celsius or 1 Kelvin is because we're going by difference between two numbers and not absolutes. Elements or compounds that have high intermolecular forces will also have high specific heat capacities. And then mathematically, Q, which is its quantity of heat in joules, is equal to the mass of the substance M. Cp is typically used for specific heat capacity. And then delta T, change in temperature. If you multiply all three of those together, you get heat. Pause here. All right, I'm going to work through this. So I've got 100 grams of water. It's originally at 50 degrees Celsius, and then I need to know how much energy to boil all of it. So there's 2 steps here. You have to think about the steps before you really do the problem. First, I have to heat that water from 50 degrees Celsius to 100 degrees Celsius. And then the second step will be to overcome the heat of fusion. Once I know what my steps are, I just do the 2 calculations and then add them together at the end. So the first one, I'm going to just need to use the equation that Q is equal to mCp delta T. Got 100 grams of water. Gave me the specific heat capacity in the question, and then it's 50.0 degree difference. I put this in my calculator and I got 20,900 joules, rounded it to 3 sig figs. And then for the second one, I don't need to use Q equals mCp delta T because I don't have a specific heat capacity and also because temperature is not changing. So I'm going to do sort of a unit conversion. So I've got 100 grams of water. I look and I see that the heat of vaporization is given in kilojoules per gram. I can just use that. Sometimes it's going to be in moles, kilojoules per mole, so you'll need to convert your grams to moles first. Not super common, but sometimes you'll see that happen. Put this in my calculator, I get 223 kilojoules. And now I add together. So I'm going to need to convert one of them to the unit of the other. So I just did turn this to 20.9 kilojoules. And then I add together. Making sure to round to the nearest one because sig figs. So I got 224 kilojoules. That is all for today's video. Thank you so much for watching and have a great night.